Welcome everybody to this HEP-TN Seminar, where we cover topics of tensor networks from high energy theory and related topics. And today we have the pleasure to welcome Andreas Bauer from nearby the Freie Universität of Berlin, who will talk about topological fixed point models. Please take it away.
Okay, yeah, thanks for having me here. I'm very glad to speak in this seminar series. So I will try to give you an insight about topologically ordered model by focusing on like what I believe is the most fundamental property, namely that path integrals invariant under arbitrary topological deformations. And I'm going to formalize this notion using the language of like path integral tensor networks, which I believe is a very natural language for quantum many-body systems. And I'm not going to talk so much about like describing realistic materials, but I'm going to talk about fixed point models, that is like toy models with zero correlation length that can be used to classify phases of matter. And the contents of the talk are like have some overlap with a paper of the same title that you can find on the archive together with Jens and Caro. Okay. So common approaches to classifying topological phases can be like divided into two groups. So one group like consists in writing down invariants, like the most like commonly known invariant of topological phases are the braiding and fusion statistics of the anyons, for example, but one might also consider the so-called axiomatic TQFT, that is like what physically corresponds to like the collection of correlation functions that fulfill a few consistency equations. So invariants always have the problem that like for a given set of invariants, there might not be an actual microscopic model which has those invariants. On the other hand, there might be the opposite problem that there are like two or more different models and two or more different phases that have the same invariants. And for this reason, we will stick to the second type of classification, which consists in writing down full microscopic models, so-called fixed point models. And those are conventionally written down in terms of comedic projector models, or in a more mathematical way as lattice TQFT or state sum models. But also this kind of second approach has a big problem, and that is that it cannot describe chiral phases in 2+1 dimensions, because we know that chiral phases do not admit for any commuting projector descriptions. So now both approaches have the problem that they're kind of formulated in terms of higher category theory, which is like a relatively complicated tool and like not very accessible to a broader physical community. So the approach that I'm going to introduce to you like is relatively similar to lattice TQFT and state sum model, but like all you need to know to understand it is really just tensor networks and tensor network notation. However, it also like generalizes these like state sum models because it allows to like systematically construct new families of state sum models. And in principle, this might also be a way to get fixed point description of chiral phases. And so if anything is unclear in the talk, don't hesitate and you can just interrupt me at any time. Okay, so since it's a tensor network seminar, I guess I don't need my 2-minute introductions to tensor networks. So I can just skip that. So indeed, Penrose notation will be like in the center of the language that I'm going to show you. And the tensor networks, like denoted by the Penrose diagrams, they will describe physical models in terms of the Euclidean path integrals. So those are not tensor networks in the sense of PEPs or MPS that describe a ground state, but those are models that live in space-time and they don't have any open indices except for if we kind of cut open some boundary. And those tensor networks obey a set of equations, or more precisely the tensors that form these tensor networks, equations of kind of this type. So these are just equations between two different tensor networks formed by the same tensors. And equations of this type will kind of be the equations that restrict our models to fixed point models with very specific properties. So on the other hand, I might also like simply forget about the tensor network interpretation and well, simply interpret the Penrose diagrams as combinatorial objects that describe combinatorially the spacetimes. And then equations like this might be interpreted as moves, which like deform the combinatorial structure by like cutting out a small piece that looks like the left-hand side and inserting the right-hand side, or the other way around. And now the idea is that if we want fixed point models for topological phases, then the combinatorial structure subject to those moves should be a discrete analog to continuum manifolds subject to homeomorphism. So I said to you that the path integral of a topologically ordered model should be invariant under like topological deformations, that is homeomorphisms. And well, as you know, quantum phases are ground state phases. And I get the ground state by cooling the system. That means applying the imaginary time evolution. So the path integral I'm looking at should be the Euclidean path integral. And now invariant simply means that if I put this path integral onto some disk, and now I apply some homeomorphism to that disk, and put the path integral on the deformed disk, then those two path integrals should evaluate to the same tensor. And it is very easy to see what that actually means formally if the path integrals are formalized as tensor networks, because then I will have kind of a tensor network inside these two disks with no open indices except for at the boundary. And those two tensor networks will evaluate to the same tensor. So now if you take a path integral tensor network coming from a condensed matter model, you can get such a thing by like trotterizing the imaginary time evolution under local Hamiltonian. But the tensor network you get will only be like defined on regular lattices, such as square lattices. So in order to make sense of this, you kind of would have to extend the definition from square lattices to arbitrary irregular lattices that you can also put on curved manifolds. So this is in general possible, but even then you would see that this equation does not hold exactly. It only holds if you add like a small buffer region in which the homomorphism is supposed to act trivially. And typically it will hold like exponentially well if we increase the radius of this buffer region. However, in this talk, we're interested in fixed point models. And for such models, the topological invariance will hold without any buffer region and in a very simple manner. And well, if you think about it, then actually, like you can see that any realistic model can kind of brought in such a fixed point form by simply zooming out and like coarse graining the tensor network by like blocking bigger patches of tensor network into single tensors. This will make kind of the characteristic length scale of this blue region here shrink and shrink until you like end up with a fixed point model. At this point, I should quickly warn you that this notion of topological deformability is not exactly one-to-one with what people commonly call topological order. So, well, conventional like intrinsic topological order in 2+1 dimension indeed has this topological deformability, and also like anything that is called SPT order, but also symmetry breaking phases have the same kind of topological deformability, even though they are not topologically ordered in a common sense. On the other hand, there are so-called fraction phases, which some people refer to as topologically ordered. However, they do not have this type of topological deformability because those are not defined on like topological manifolds, but on foliated manifolds, and they have a slightly different type of deformability. Okay.
Can I ask at this point? Oh, yeah. Is it correct that topological effects are very dependent on the space-time dimension? And are you, since this intuitively looks particularly like 2 dimensions, are you restricting yourself to two dimensions for these statements, or?
No. So for the sake of the talk, I will present everything in 2 dimensions, but everything should like carry over very straightforwardly to higher dimensions. So in particular, this property should also hold in any other dimension. And kind of the formalism I show you like looks the same in any dimension.
Okay.
Exactly. So tensor networks are something discrete. Thus, they also need a discrete representation of the manifolds. So in 1+1 dimensions, which I'm sticking to for this talk, this can be achieved by describing a 2 manifold via a triangulation. And now you need to put a tensor network onto the triangulation, and the easiest way to do this is to take one and the same tensor and put it on each triangle and then contract indices between neighboring tensors. Okay, now we also need a combinatorial analog of like homeomorphisms, and a simple way to do this is via the so-called Pachner moves. So in 1+1 dimension, they look like the following. You can, for example, like exchange 2 vertically separated triangles by 2 horizontally separated triangles. And so now invariance of path integral under these moves simply means that, well, if I put my tensor network in both of these disk-like patches of manifold, they should evaluate to the same thing. So I get like 2 equations between 2 different tensor networks formed by this 3-index tensor. And now at this point, I would like to make a difference in language between like the combinatorial structure of these networks themselves, like these Penrose diagrams modulo these moves, and which I will call liquid, and the actual tensor, the 3-index tensor that like fulfills these equations, which I will call a model of the liquid. And such models are then like fixed point models in a physical sense that they describe like path integrals of topologically ordered systems. Okay, so now the natural next step would be to look at like what these models are. But before that, let me quickly like generalize this construction by giving each edge an orientation, and also demanding that around each triangle, this orientation is non-cyclic, which is then called a branching structure for the triangulation. This allows me to distinguish the 3 different edges of the triangle, which I then denote in my Penrose notation by like putting small flags near to where the indices are connected to the tensor shape. And if I do this, I also have to equip my Pachner moves with edge orientations, and I can do this in various different ways. And in fact, if I want full topological invariance, then I have to like impose the tensor network equations corresponding to all these different edge orientations of the different Pachner moves. So this will yield like a very complicated and big set of equations. However, one can like combinatorially simplify those equations and get an equivalent like simpler set of equations by kind of going to cellulations by not only triangles, but also other kind of types of cells. And then what you end up with is essentially one single of these Pachner moves together with a bunch of simpler equations. But I won't go too much in detail there. Instead, I will ask the obvious question, why would we want to introduce these edge orientations? And well, a simple answer is it doesn't hurt, like the combinatorial structure with these edge orientations still describes topological manifolds. However, like without the edge orientations, in these diagrams, there's no way to distinguish the 3 indices of a tensor, which implies that each tensor is invariant under arbitrary index permutations. And by introducing this branching structure, this restriction to the tensor is lifted, so I will get more general models like this. But there also like, I would also like to give you 2 more like sophisticated arguments why we should introduce a branching structure. So one is that I told you that like the combinatorial structure of these like of these networks should correspond to continuum manifolds. However, if you look at the Penrose diagrams without this branching structure, then you see that those diagrams are nothing but three-valent graphs. And from this three-valent graph, so this graph tells you which triangles share a common edge, but it does not tell you which edges they share, and it does not tell you in like which directions the two edges are glued. So for example, if you consider this graph here consisting of two triangles, then depending on how I glue the edges together of the triangles, I can obtain either a sphere or a cross-curve or a torus or a Klein bottle. So this is not a good faithful representation of like two manifolds. And this problem is lifted if I introduce a branching structure, because that allows me to like distinguish between the different edges, and it also fixes in which direction I glue two edges, because the orientations have to align. The second argument is that, well, we would have to have a fixed point form that is general enough such that every like topological path integral can be zoomed out and blocked into this fixed point form. So this means that like if I take any topological path integral, put it on like a large patch, and then I evaluate the tensor network of this non-fixed point path integral on this large patch. And I like group the indices corresponding to each edge here. Then I obtain a single like triangle tensor of a fixed point model. However, when I group indices together, I always have to do this with respect to index ordering. And in order to canonically fix this index ordering, I have to introduce an orientation of these big edges here. Okay, is everything clear yet? Are there any questions? Okay.
Yes, I have a question.
Yeah.
Hi, Andy. So by this last picture, do you mean that zooming out doesn't change the tensor, or that by zooming out you get closer and closer to your fixed point?
Yeah, the latter.
Because the latter, okay, because the former would be something like intuitively I would connect it to conformal invariance or something. That would be something different.
Mm-hmm. Yeah, okay. So by zooming out, I mean like you block a huge patch of tensor network into a single tensor. And then this tensor you get will be more and more like topologically invariant. In fact, the same you can actually also do with CFTs.
Okay.
Like the idea is not so different. Yeah.
Okay.
And obviously, this dimension here will like grow like massively if you do that. So if you want to turn that into a practical algorithm or anything, you would have to like truncate this dimension here.
Okay. Thanks.
Okay. Okay. So, well, we kind of enriched our like liquid combinatorial structure by a branching structure, and now there's only one more last step we need to include to get like a physical fixed point like construction, and that is we have to introduce an orientation, because like commonly quantum mechanics likes to live on oriented manifolds and not only on manifolds. This can be done combinatorially. So by noticing that if we have an orientation, then for each edge of a triangle, we can say whether it's oriented clockwise or counterclockwise. And this allows us to distinguish between like clockwise triangles with both edges, like where two edges are oriented clockwise, and counterclockwise triangles where two edges are oriented counterclockwise. And so all we need to do in order to incorporate an orientation into a combinatorial structure is to use a different symbol for the clockwise edge triangles than for the counterclockwise triangles. And here the symbols differ by like the number of in-pointing arrows, which represent like clockwise edges. And for the models, this means that the tensor we associate to clockwise triangles is different from the tensor we associate to counterclockwise triangles. So as you all know, quantum mechanics is Hermitian. That means that the Hamiltonian as a matrix, if I exchange it to indices, this is the same as complex conjugation. So if I view the Hamiltonian as an operator that kind of acts in a time direction, so here, for example, for like a two-body operator, this means that if I kind of invert time direction, then this is the same as doing a complex conjugation, which I like denote in this tensor network notation by encircling everything that is conjugated by this zigzag line. So now, in fact, the same property also carries over to the tensors of the imaginary time path integral. And now for the fixed point tensor network, however, there simply is no time direction, because like lives in an Euclidean space and all directions are equal. However, inverting any direction still corresponds to inverting the orientation. So that means for fixed points, hermiticity means that if I invert the orientation, this is the same as complex conjugation. So for the model, this simply means that the clockwise triangle tensor is the complex conjugate of the counterclockwise triangle tensor. Okay, so this is a full kind of like fixed point axioms, and now we can look for like models of these axioms. And well, we can get inspirations from the fact that these axioms are very similar to the axioms of associative algebras. So this brings us to the conclusion that like all models essentially fall into like two types. So the first type of models is given by delta tensors. So tensors that have entry 1 if all indices are in the same configuration and entry 0 otherwise. So in other words, this is a tensor that like forces every index to be in the same configuration. So if we build like a space-time tensor networks out of tensors like this, what we will get is something like every index globally is in the first configuration plus every index globally in the second configuration and so on. So this is like a GZ type entanglement, and that's the stuff that you have in symmetry breaking phases. The second type of solutions is inspired from like n times n matrix algebras. So the corresponding tensor is just like a tensor product of 3 identity tensors, but the open indices are kind of blocked together in a non-trivial way. So now you see if you kind of insert a matrix at one of these double indices and another matrix at the second double index, then you see that you will contract the second index of the first matrix with the first index of the second matrix. So this is exactly what you do when you do matrix multiplication. So this tensor is associated to a triangle. So we see that in every like corner of the triangle, we get one of these identity tensor arcs. And now if you build the tensor network, the corresponding tensor network on some triangulation, you will see that around each vertex, these arcs of the corners around the vertex just build a loop that is disconnected from the rest. And that can be evaluated to a number, which is nothing but like the bond dimension of this identity tensor. So this tensor network is equivalent to nothing but a product of numbers. So as a physical model, this is completely trivial. It doesn't have any degrees of freedom even. But in the end, what it boils down is like a classical invariant. In fact, just the Euler characteristic of the manifold. So this is not very surprising because, as you know, there isn't any like non-trivial intrinsic topological order in 1 + 1 dimensions. But this is, however, only true for like spin systems. For fermionic systems, you will see that there are like other phases, or also for like phases protected by symmetries that are non-trivial phases. And also these kind of cases can be described in this framework. In fact, I can simply use the same equations. I just have to change my interpretation of the Penrose notation. which means I have to like associate a different meaning to what the tensors are, what the contraction is, and what the tensor product means. But this meaning has to still to be consistent with the graphical calculus. And I will like call such a different meaning of the graphical calculus a tensor type, and those different tensor type like formalize different types of matter. So to give a very few simple example, so consider spin systems that are protected by a time reversal symmetry. That means like an anti-unitary, that two symmetry. And every such anti-unitary that squares the identity can be brought into a form where it is only complex conjugation via basis change. And tensors invariant under complex conjugations are just real tensors. So in order to get models for topologically ordered spin systems protected by time reversal symmetry, we just need to look at the same equations and interpret them in terms of real tensors. And now you might think, oh, well, real tensors are kind of more restricted than complex tensors, so the models will be even more boring. However, when I told you that all solutions, all models kind of look like this, what I actually meant is that every model is isomorphic to a model of this form. That means that if I apply one and the same unitary to every index, I can bring the model into one of these forms. But now, if I restrict to real tensors, I'm also not allowed to use unitaries. I can only use orthogonal matrices as basis changes. So it can happen that there exist like models that are in the same phase and like isomorphic as complex models, but which are not isomorphic as real models. And this actually is a case in this example. So there's one more real model that corresponds to the quaternions. So the quaternions are a four-dimensional real algebra. And this four-dimensional real algebra like yields a model. And this is not equivalent under real basis changes to one of the models from the slide before. It's only equivalent if I allow for complex basis changes. Okay, I can also like describe models with like an ordinary unitary group symmetry. There I just have to use something like some variant of tensors where each index is not only equipped with a bond dimension, but also with the representation, such that the tensor is invariant under all of its representations. And now, like if I contract two indices, not only the bond dimensions have to agree, but also the representations, which ensures that like contraction is compatible with the symmetry constraint. And if I look for different ways to equip these tensors with symmetries, then in this case, well, I get conventional symmetry breaking order. And in this case, I recover the cohomology classification of SPT phases. And the same way I can also do fermions by kind of using some like super vector space variant of arrays. However, the fermionic case is a little bit different because in the fermionic graphical calculus, you have to equip all the contractions with directions. Okay, so we've seen that the same equations can be interpreted in terms of different tensor types to get like models for different types of matter. But also I can just like write down different equations. And well, for example, I can do this triangulation way of finding combinatorial structures in any dimension higher, but I can even also do this to describe fixed point models for topological boundaries or fixed point models for any sort of defects like onion world lines. But what I can also do is I can look for alternative combinatorial like representations of the same thing. So, and this was like 2 manifolds for this talk so far. For example, one simple toy example is I can put a tensor on each edge of a triangulation instead of each triangle, a 4-index tensor, and then I contract all these tensors like I depicted here. And now for this new combinatorial representation, I also need new moves. In principle, I could just like write down kind of Pachner moves in terms of this edge combinatorial structure. However, it turns out that there's a set of moves that is much more well suited. And the kind of most important of these moves is a move that like takes one edge and slides the endpoint of like this edge along another edge. Don't worry about these decorations here on the edges, they're just needed to like introduce an orientation again. So in terms of networks, this like yields the tensor network equation on the right between like two networks formed by two of these edge tensors. Well, another move I have to introduce is a move that allows me to get rid of like a dangling edge, so an edge which has an endpoint that is not connected to anything else. And if I impose the tensor network equation on the right, this implies that I can do this deformation on the cellulation that I've shown you on the left. Okay, so now I found a different combinatorial structure, also representing two manifolds, or actually oriented two manifolds. And also the solutions to those equations will correspond to topological fixed point models in 1+1 dimensions. So the natural question is now, are these models any different from what I found earlier? And well, of course, they're different. They're given by different types of tensors. Those are really microscopically different tensors, and they might be kind of usable or more useful than the other models for specific practical purposes. However, for the purpose of classifying phases, the relevant question should be, do these models describe any more general phases? And in this case, this is not true. And one can see that on a purely combinatorial level, because there is a way to like express the edge combinatorial structure in terms of the triangle combinatorial structure locally and vice versa. So I can simply replace any edge by like two triangles. Like if I do this to a cellulation, this has kind of the effect of adding a central vertex to every face and then kind of dividing this face into like triangles, like you would divide a cake. In terms of tensor network, this amounts to like replacing any of these like edge tensors by a network formed by two triangle tensors. So for the model, this equation means that for any model of the triangle liquid, evaluating this tensor network will yield a model of the edge liquid. And for this to be the case, actually, this kind of replacement has to be consistent with the moves. So that means if I plug in this replacement into one of these moves of the edge like liquid, then what I get is an equation between like two big tensor networks of this triangle liquid. And this equation will not be directly a move of the triangle liquid, but will be equivalent to a sequence of those moves. Okay, so now I also have an opposite mapping that like maps the triangle combinatorial structure into the edge combinatorial structure by simply replacing each triangle by two of its edges. So in tensor network languages, what this yields this equation, which again means that for any model of this edge liquid, I can evaluate this tensor network and then I block together A and A prime and the indices B and B prime and C and C prime, and then this yields a tensor of the triangle liquid, which is again a model of this triangle liquid. And again, this kind of replacement is consistent with the moves. So now there's one more thing that I need to add, or one more property of these two replacements, which is that they are inverses to each other. But they are kind of not inverses in a direct sense, but in a kind of a weak sense. This means that if I start with the say a network of this edge liquid, then I apply the first mapping, and then I apply the second mapping. I do not end up with the same network, but I end up with a network that is equivalent to the original one up to these local moves. And this implies that if I apply these two mappings to a model, I do not end up with the same model again, but I do end up with a model that is in the same phase. So you see that the models of the two liquids are the phases of those models are in one-to-one correspondence. So they describe the same phases. Are there any questions so far? Or is everything clear? Okay, then I'll go on. So, well, now you might think clearly they are in the same phases because, well, it shouldn't be a surprise because they both kind of describe two manifolds. However, this is not the case. And actually, we've already seen like another liquid describing two manifolds, namely the one without branching structure, which is also not equivalent to these kind of liquids. And in fact, I can write down like liquids that are even more general than this and allow for even more phases. And this is in particular because when I earlier said to you that any model can kind of be zoomed out and coarse-grained into a model that has this kind of branching structure, triangular form, I was actually lying to you because this doesn't work. And the reason why this doesn't work is, well, it can kind of have like tensors that are directly in the corner of this like large zoomed out triangles. And there's no way to kind of homogeneously split up this tensor at the corner into tensors that would correspond to the individual triangles. But however, there are other forms of combinatorial structures that do have this property that any like path integral can be zoomed out and blocked into them. And well, one is as simple as like saying that we put a tensor on each vertex, such that the tensor network itself looks the same as the diagram of kind of the triangulation. So this might look simple, but we notice that a vertex can have a different number of adjacent edges. So actually, for each such number, we have to define a different tensor. I mean, you don't have to like write down an infinite amount of tensors to specify such a model. Every manifold can be triangulated by, say, up to 7 nearest edges. And then the moves of this kind of combinatorial structure also look pretty complicated. They're essentially like Pachner moves, but I like denote them by replacing every vertex by a tensor. Yeah. So I've shown you a kind of combinatorial structure that is not equivalent to the triangle liquid. So no matter how much you coarse-grain this, you will never be able to bring it in a form that corresponds to a triangle liquid, which means that, well, possibly the models of this kind of combinatorial structure, the solutions to these equations, can have more general phases. And one way also to see that this is not combinatorial equivalent is like to consider like what the tensor network would look like on a vertex with a lot of adjacent edges. So for the vertex liquid, there would be kind of a vertex in the middle. And it is possible that there's no way to kind of homogeneously split up this tensor in the middle into tensors that live on the individual triangles. Or another way of saying it is that if you want to define this triangle path integral, this vertex path integral by only a finite amount of tensors, you have to restrict to a upper bound in the allowed adjacent edges. There is no way to locally like resolve such a vertex with arbitrary many adjacent edges into a network with vertices with a bounded number of adjacent edges. For this, you would kind of at least need a logarithmic sized network. Okay, so well, while it's always possible that you can get more phases, this is not a must. And in fact, this also depends on the tensor type in which you interpret these equations. And one can actually always write down like artificial tensor types for which you actually get like new phases. However, for physical tensor types in 1+1 dimensions, this is not the case. And this is simply because, well, like phases in 1+1D are essentially classified also away from the fixed point, and there's simply no like new topological phases there to expect. Another reason why this is not the case can be seen as follows. So this triangle liquid I've shown you is actually not a universal fixed point in the sense that any topological path integral can be blocked into it, but every path integral that also has a topological boundary can be blocked into this form, which is not true for this more general vertex liquid. However, in 1+1 dimensions, there isn't really a notion of like a gapless boundary, because the boundary is like a 0+1 dimensional object, and like gaplessness in the sense of criticality or conformal field theory is like a 1+1 dimensional thing. So I mean, sure, people do speak of like gapless edge modes for 1+1 dimensional systems, but what they actually mean is like degenerate edge modes, which are still gapped. So we won't find any new phases in 1+1 dimensions because their all boundaries are gapped and therefore topological. However, it is possible in 2+1 dimensions that boundaries are not allowed to be gapped. And this is exactly what we have for chiral phases. And this is why like chiral phases are quite kind of a hot candidate to be kind of described by this more general type of fixed point models. There's also another thing that indicates that this might be possible, namely that this kind of triangle form of liquids does not only have a standard boundary construction, like a construction for a standard topological boundary, but it also has a construction for a commuting projector Hamiltonian, which is not the case for like general models of this more generalized liquids. And as I told you in the beginning, chiral phases are known to not allow for any commuting projector Hamiltonians. So this kind of more general like way of combinatorially representing manifolds allows to kind of circumvent this no-go theorem. Okay, so to wrap up, I showed you like how to like construct fixed point models from combinatorial representations of spacetimes by simply interpreting the combinatorial structure as tensor networks. And this same like language can be applied in any dimension. It can also be applied for like fixed points of boundaries of models, or anionic world lines or domain walls or any sort of other defects. You can also add extra structure like an orientation, or for fermionic systems, you want to add a spin structure, which can also be described combinatorially. And by like choosing different interpretations of the tensor network, of what the tensor networks mean, I can also describe like fermionic models or models with symmetry. And this also yields kind of a more direct understanding of why existing fixed point models, such as the Kitaev model or the Trotterization models, have the exact form they have. From the space-time picture, you can see relatively easy that you, for example, need this branching structure if you want to like have something that other models can be blocked into. This also helps to like get the correct technical details of like existing fixed point models, because we kind of turn around the direction here. We do not like take an algebraic structure, which we kind of guess as an input to a construction, but we directly start with the central property which we want. We kind of derive an algebraic structure from there. And well, on a practical level, what's probably the most useful about this formalism is that you can kind of systematically construct new families of microscopic models, and even they might describe the same phases. They might be useful for practical purposes, such as error correction, or if you want to kind of engineer them in the real world with like a given set of components. And then we've seen that it's also possible to write on more general like equations, which like possibly allow for more general solutions. And a hot candidate for this is chiral phases. And last but not least, one might also look at other types of deformability, such as like a fractonic kind of deformability, or maybe even like conformal deformability for critical models. Okay, well, that's it from my side. Thanks for listening.
Thank you very much for your talk and virtual applause. Yeah, we have time for questions, so if anyone has a question, please simply speak up. Maybe let me actually start regarding the first point of your summary in particular. So yeah, there are examples where topological effects play a role. Maybe could you elaborate a bit more where such in realistic physical systems where such topological effects or phases appear in actual effects, or maybe even real world materials? So in which case this approach that you presented would be especially, or could be applied in particular?
I mean, like all these kind of fixed point or exotic topological phases are not phases that you like super easily find in nature. So I guess the phases that are actually actually found in nature, so for like fractional quantum Hall systems, which are chiral models, and therefore like you cannot describe them with like common fixed point models. But I mean, these are kind of systems such as the Tori code, which are also interesting for quantum information purposes, because you can do topological quantum computation with those models. So kind of those phases are not only phases which you might find in nature, there are more phases which you might want to engineer for quantum information purposes.
Maybe a bit in that direction, since the starting point is a triangulation, if I understood it correctly. Could you use this framework where you associate a tensor network to that triangulation for any curved space-time geometry, so that you yeah, have a tensor network representation for given curved space-time?
Exactly. So kind of the model, this fixed point model is a tensor network, so a path integral that you can put on any manifold, like any triangulation of any manifold. So this is arbitrary space-time geometries.
Could one consider also use that to discretize a given quantum field theory model, for example? Like, I don't know, Phi to the model or whatever.
Yeah, so these are in principle like discretized versions of topological quantum field theory, and like, for example, Chern-Simons theories. So yeah.
One can consider that also in the continuum limit, or like take continuum limit for that.
Yeah, I don't know exactly how to formally like from this tensor network get like a field theory description. I don't think there's like a general like formalism or a general way to proceed in that direction, because I think this kind of discrete way of formalizing is in principle kind of more general than a field theory way. But there's kind of the opposite direction should be doable easier. So you can kind of think of like discretizing a field theory by kind of putting it on finer and finer lattices, and then you kind of choose a fixed unit cell in space-time and consider kind of the field theory inside that unit cell, and this will kind of block into, this will use the tensor. And well, so yeah, in principle you can discretize field theories to get such a like tensor network path integral. So that way around should work. The other way, I'm not sure. I don't think that general methods, but yeah.
Other questions?
I had a question about Hamiltonians. So I know for a triangle liquid, you can form the two local term of the Hamiltonian out of two triangles side by side.
Exactly, yeah.
Right. And I guess the Pochner-Mears imply that that thing is a local commuting projector Hamiltonian.
Exactly. So the commuting projector equations follow from the topological invariance. Yeah.
Right. So for something like a vertex liquid, do you have a Hamiltonian, and can you see that it's not a local commuting projector in general?
Mm-hmm. You do not get there's no standard construction for a Hamiltonian, but I'm pretty sure that you can. So there's no like direct way to get a Hamiltonian. I'm pretty sure that you can probably like define these tensors not only for different numbers of adjacent edges, but also kind of for different angles between these edges, and then consider kind of some limit of where these angles go to zero. You know, like there are these constructions in CFT or in integrable models such as the critical easing model, where you can kind of construct a quantum Hamiltonian from these critical models satisfying the Yang-Baxter equation. And I would think that something similar is possible here, such that you kind of get a local Hamiltonian that, however, is not a commuting projector model. But
okay.
I'm not entirely sure how to do it. Yeah.
So if you were interested in topological things where you couldn't take into account the angle, there's still not a standard form for like a two local term in the Hamiltonian.
Yeah, again?
So in the special case of topological phases where the Hamiltonian should be independent of any angles, there's not a way to extract the Hamiltonian from the tensors assigned to vertices.
Oh, I see. No, yeah, I don't know exactly how it would work, but I think that you might also be able to like do a similar construction as in this critical case to like kind of define terms for smaller angles. And I don't think this directly contradicts the idea that you have a topological theory. Yeah, but I don't know exactly how this works. Yeah.
Okay.
I mean, from a fundamental point of view, in my opinion, I don't think we really need Hamiltonians. They can, in principle, view this kind of path integral way of describing a model as a totally independent formalization of quantum mechanics. And yeah, can in principle say that that's good enough for me if I got this path integral.
I see. On the level of just topological invariance, then for the space-time manifold, do you know of any invariance that can be discretized as a vertex liquid that cannot be discretized as a face liquid?
Oh yeah, there are actually examples of this. So like for classical invariants, so classical invariants are kind of contained in this picture where the tensor networks are not actual tensor networks, but just like products of scalars.
Mm-hmm.
Actually in 3+1 dimensions. The signature of a manifold is an invariant that, well, you cannot represent this on a triangulation by just putting a number on each tetrahedron, but you can like represent this by putting a number on each vertex. And the number you put there depends on the link of that vertex, so kind of the surrounding of the vertex in the simplicial complex. And this formula, this dependence of this number on the link, is such that like this number cannot split up homogeneously on like a term for each of the surrounding tetrahedra.
Okay.
For simplicity,
so this is like a Walker-Wong model, and it would fit in formalism as a vertex liquid.
Exactly. Yeah. So this is kind of what the Walker-Wang model, like conjecturally, can be like is equal to, like for a modular input.
Mm-hmm.
So the Walker-Wang model in 3+1 dimensions one should be able to kind of like disentangle it into a tensor network of this simple scalar product form. And this, but obviously that's kind of physically a trivial theory because there are no degrees of freedom.
Mm-hmm.
Yeah.
Okay, thank you.
Cool.
Okay, very good. Are there some further questions?
Yes, I have a question relating maybe more to the field theory question from the beginning. Namely that, are there any restrictions on local dimensions of the link? So, because if I imagine a field theory, there might also be like infinite dimensional Hilbert spaces, which, yeah, are they included or do you have to approximate them when putting them into this tensor network language?
So, so the models I have in mind are all in finite dimensions of the Hilbert spaces. In principle, you could think about infinite dimensions, but then kind of, yeah, the interpretation of Penrose notation is a bit funny in infinite dimensions because you cannot simply contract over any pair of index. So you kind of would need some condition of like the tensor entries decaying with like increasing like configuration number of the indices, and you would kind of need a decay condition that's kind of consistent with like
so sort of built-in regularization, or what kind of?
Yeah.
Okay.
Yeah, I mean, I kind of suspect, I mean, I really don't know anything about regularization, but what I kind of...
Yeah, me neither. It's just intuitively.
Yeah, so what I kind of intuitively suspect from what I heard about regularization, I think it might like boil down to the fact that you can like discretize a field theory in a tensor network locally.
Yeah, that makes sense. Okay.
Okay, if someone else has a question, simply speak up. If that is not the case, then let's thank Andy again for the nice talk.
Thanks for listening.